Hello everyone, welcome back in the course of Higher Surveying. We are in lecture 3 of module 7, that is LiDAR grammetry. In the last lecture we learned that how to acquire the airborne LiDAR data, terrestrial LiDAR data and mobile LiDAR data. So we have given different names like airborne LiDAR, terrestrial LiDAR and mobile LiDAR scanning. Also we came to know that in case of airborne data acquisition, in addition to the laser scanner, we have to have the IMU as well as GPS so that we can find out the 3D coordinates of the aircraft trajectory, and using that trajectory we can find out the 3D coordinates of the points on the surface of Earth where laser pulse is interacting. In this lecture we are going to learn the process of georeferencing, which means we bring the complete data into one reference frame, and that reference frame is ITRF or International Terrestrial Reference Frame. The process of bringing the LiDAR data into the ITRF reference frame is called geolocation. So let us go ahead in this lecture. So we are in lecture 3, that is geolocation and errors of LiDAR data. Now in order to understand the geolocation process, we need to define some reference frames. So we have 5 reference frames, and that will connect the basic measurement of the laser pulse to the ITRF reference frame. First is instantaneous reference frame, then we have scanner reference frame, then we have body reference frame, earth tangential reference frame, and finally geocentric reference frame or international terrestrial reference frame. And we need to only do the translations as well as rotations among these reference frames. First of all, instantaneous reference frame is there, and you can see that there is an aircraft, and aircraft is mounted with the laser scanner, IMU and GPS. GPS determines the trajectory of the aircraft and it acquires the data at every 1 second. During that 1 second, we take help of the IMU, which measures the roll, pitch and yaw with respect to the true north, true east and the gravity direction. So using that 3 angles, we try to find out the aircraft trajectory coordinates during that 1 second where GPS could not acquire the data. So we can understand that we have the continuous data of the GPS trajectory. So with this understanding, now let us look into the animation. There is a plane and there is a terrain, and now the laser scanner is going to acquire the data like this. These laser pulses are fired on the surface and these are reflected back to the scanner, and the scanner has received them, determined the range R and the scan angle eta. What is the scan angle? Scan angle is the angle of a laser pulse with respect to the vertical. So let us consider one point on the surface of Earth, and this is the laser pulse. Let us define the instantaneous reference frame. So in case of instantaneous reference frame, the x-axis is in the flight direction, or the nose of aircraft, and what about the z-axis? So z-axis in the direction of pulse. What about y? Y is framing the right-handed coordinate system with x and z. So now there is a laser pulse here, and so we have defined the instantaneous reference frame like this. Now let us define the scanner reference frame, which is like this. The x of the scanner reference frame and x of the instantaneous reference frame are same in the flight direction. Then we have this z direction of the scanner reference frame in the direction of vertical or gravity direction. Then what about this y axis? So y axis is again forming the right-handed coordinate system. I am writing in short, right-handed coordinate system with x and z. So this is scanner reference frame. You can notice here the origin of the reference frame at the laser scanner. Moreover, I would like to say one thing here, that we are using the term reference frame, which means it is not a theoretical concept, it is a realized reference system. That means I know the origin of the reference frame as well as the orientation of the reference axes. So that is why we are using the word reference frame. So this is the scan angle eta. So we defined this scan angle in the last slide also. So this is the angle of laser pulse with respect to the vertical. So this direction here, gravity direction here. Let us understand the body reference frame. We are showing the scanner reference frame in blue color, and now I show the body reference frame located at the IMU like this. So in this case, direction of the IMU reference frame or the body reference frame at IMU and scanner reference frame are more or less well aligned. That means their orientation axes are in the same direction. There could be slight difference, and this difference is around 1 to 2 degrees only in each 3 axes. So that is called the body reference frame. One thing about IMU we should understand, that IMU, when it is set up in the aircraft, it is put in the switch off mode. What is switch off mode? It is turned off, it is not turned on. As a result, when it is commissioned in the aircraft, it is indicating the X direction in the nose of aircraft and Z direction here, Y direction here. The moment it is turned on, these 3 axes will indicate the true north, true east and the gravity direction at a particular point. That means when aircraft is flying on a certain path, at that point of aircraft trajectory, the switch on IMU will indicate the true east, true north and the gravity direction. And now if we measure these 3 angles, that means the IMU switch off position and IMU switch on position, the corresponding angle between the 3 axes will be the roll, pitch and yaw. And so they will help to convert scanner reference frame or body reference frame into the other frame. So that other frame will be the earth tangential reference frame. So this is earth tangential reference frame, where we are showing one aircraft and that is following a trajectory like this. So at this point where aircraft is right now, we have fired a laser pulse towards the point P on surface of earth. This is the aircraft trajectory. This is the projection of this trajectory on the WGS-84 ellipsoid. I am defining a local geodetic horizon system here. So now you can see there are 2 angles, phi g, which is the geocentric latitude of the aircraft position, as well as lambda, which is the geodetic longitude of the aircraft position here. So let us define this local geodetic horizon reference frame. I am also defining the same plane at this aircraft trajectory point here, parallel to this plane. So we know that this is the true north, this is the true east, this is the gravity direction here. And so we are defining the same orientation of the reference frame at the aircraft trajectory like this, true north, true east and the gravity direction. Here we have taken an assumption that this direction is the gravity direction, but it is matching with the geocentric latitude. In most of the areas, this is very fair assumption for the earth surface if we are using the WGS-84 coordinate system or ellipsoid. In certain areas, if this assumption is not fair, we should conduct some special study to find out the deviation between the gravity direction and this direction, which is indicated by the geocentric latitude. So this is earth tangential reference frame. Now define the geocentric reference frame. In case of geocentric reference frame, we have the ITRF or International Terrestrial Reference Frame, that is rotation axis Z, this is the X axis and this is the Y axis, and this is International Terrestrial Reference Frame. And now we want to find out the coordinate of point P, which is XP, YP, ZP in this reference frame using information obtained by the laser pulse. So that is the introduction about the reference frames, and now we are going to convert the reference frames into another reference frame by simple processes of translation and rotations, but that process has some linkages. So try to see those linkages now. The first step of the geolocation process is to convert the instantaneous reference frame located at the scanner into the scanner reference frame, which is also located at the laser scanner. So, this is the laser pulse. In the instantaneous reference frame, the coordinate of a laser pulse x, y, z is equal to 0, 0, r. What is r? R is the range. As we already told that laser scanner measures the range and the scan angle. And range is r. So, using the range and scan angle, I would convert this range to the scanner reference frame. So, how can I do it? This is scanner reference frame where it is x, it is z and it is y. And the angle between the two reference frames is angle, that is scan angle for laser pulse. If I rotate instantaneous reference frame into the scanner reference frame like this, it will convert this coordinate of instantaneous reference frame to the scanner reference frame. So, I can write that x, y, z of the scanner reference frame is equal to rotation about x axis by angle eta, and since it is anticlockwise rotation, and so I am using positive value here, and I can write here x, y, z of the IRF instantaneous reference frame or Rx eta 0, 0, r. So, that is x, y, z in the scanner reference frame. What about the Rx eta? It is 1, 0, 0, 0, 0, cos of eta, sin of eta, minus sin of eta and cos of eta. So, this is Rx eta. We have rotated instantaneous reference frame in anticlockwise manner like this about x axis. So, this rotation is happening here. This rotation is converting the instantaneous reference frame into the scanner reference frame. Let us go ahead and try to convert the scanner reference frame to the body reference frame. As I already told that as such there is no difference between the orientation of scanner reference frame and the body reference frame, but the origin is different and there could be slight difference of maybe 1 degree or 2 degrees. These values are the bore sight values, and these bore sight values are determined before we start the airborne mission, and they are also determined after the airborne mission, because it is quite possible that the orientation between the body reference frame and scanner reference frame may change because of the aircraft motion during the data acquisition, and as a result we observe it afterwards as well as we observe the bore sight values before the airborne data acquisition, and we take the average value of the two. Now, we orient scanner reference frame into the body reference frame. What is the reason here? When IMU will be switched on, it will indicate the direction of Earth tangential reference frame, and if scanner reference frame is aligned with the body reference frame, I will be able to convert the scanner reference frame to the Earth tangential reference frame. So, that is the purpose. So, let us align the scanner reference frame into the body reference frame by 1 or 2 degree, and we are indicating by some vibration here in animation. Let us see, we have alpha 0, beta 0 and gamma 0 as bore sight values about x axis, y axis and z axis respectively. So, x, y, z in the body reference frame is equal to Rz gamma 0, Ry beta 0 and Rx alpha 0. So, x, y, z in scanner reference frame. So, now you can express it like this. I am writing it in a combined form, the complete single matrix alpha 0, beta 0, gamma 0, and then I am expressing Rx eta into 0, 0, r. So, this is the coordinate of the laser pulse in the body reference frame. You can put this value here, this complete value. this is scanner reference frame coordinates. So, we have converted the coordinate of point P to the body reference frame. So, before switching on the IMU, we would like to convert or translate body reference frame which is located at the scanner to the GPS, because GPS is measuring the aircraft trajectory. So, let us do this translation by the lever arm. So, this distance between the GPS and the scanner is the lever arm or lever arm offset, and it is given by in 3 directions as Lx, Ly, Lz. Lx, Ly and Lz measured in the body reference frame. So, now I can write here x, y, z of body reference frame origin at GPS is equal to Lx, Ly, Lz plus x, y, z body reference frame origin at scanner. Now, if I write it in elaborated form, x, y, z body reference frame is equal to lever arm Lx, Ly and Lz. I am just writing it here BRF because they are measured in the body reference frame, plus rotation alpha 0, beta 0, gamma 0 by both side values. Then we have rotation about x, beta, and then we have 0, 0, r. So, this is measurement in the instantaneous reference frame here. The values are indicating the connection between the scanner reference frame and the body reference frame. Let me write here that origin at GPS. So, we have body reference frame located at the aircraft trajectory, and the body reference frame is aligned with the IMU. So, an IMU is in the switch off position or turn off position right now. If we turn on the IMU, it will indicate true north, true east and gravity direction. GPS is measuring x0, y0 and z0 coordinate of the aircraft trajectory here shown by the red color. We have already defined earth tangential reference frame. This is local geodetic horizon, and I have defined again here, and this is the 3 directions indicating the gravity here, true north and true east here, or the geodetic north, geodetic east and the gravity direction here. We have made an assumption that this direction is gravity and it is fair assumption. So, this is true north, true east and gravity direction at the GPS. Now, I want to bring the body reference frame to the earth tangential reference frame, and for that purpose, if we turn on the IMU, it will indicate these 3 directions: true north, true east and gravity direction. And surprisingly, x direction is this after turning on, this is y direction and this is z direction of the IMU or earth tangential reference frame. If I want to bring body reference frame to the earth tangential reference frame, I can write here x, y, z in ETRF is equal to r omega phi kappa x, y, z of body reference frame. So, now we can also write here what is r omega phi kappa. It will be r z kappa, r y phi and r x omega. So, now we have brought coordinate of a point P to the ETRF or earth tangential reference frame and origin at GPS. Again, this is ETRF frame. So, true north, true east. So, this is a 90-degree angle, and now I want to bring this earth tangential reference frame to the geocentric reference frame. This is z direction here, and what is the angle here? This is phi g angle, which is written here. So, total rotation about the y axis between the z axis of ETRF and this z axis of the ITRF is equal to 90-degree plus phi g. So, let us do the rotation about the y axis like this 90-degree and then this 90-degree plus phi g. Z axis is aligned now. So, I can write here the first rotation we have rotated about the y axis. Now, we will rotate about the z axis. This is x axis, this was a y axis before, x axis after rotation, and this is z axis. This is parallel to capital X here, this axis is same, this axis is parallel to capital Y axis here, and now you can see that this angle here is lambda. Let us rotate about z axis by minus lambda like this. So, now we have the rotation about z axis by minus lambda. So, x, y, z, it is in the ITRF, but origin is at aircraft trajectory or GPS, is equal to r z minus lambda and r y pi by 2 plus phi g, and then we have x, y, z, E T R F. So, here origin is still the GPS, that is aircraft trajectory. Now, both reference frames are parallel to each other, but origin is GPS. So, I will do the translation now like this. This is translation by this value x0, y0, z0 here. X, y, z in the ITRF and origin at the geocenter is equal to x0, y0, z0 plus x, y, z ITRF origin at GPS. Now, we can elaborate all these terms. So, this is the xp, yp, zp I got here, it is xp, yp, zp, these coordinates. So, let us write the equation of the translation and rotation between the instantaneous reference frame to the ITRF into elaborated form or the complete form. X, y, z in ITRF, origin at geocenter, or I can write here xp, yp, zp equals to x0, y0, z0 plus r z minus lambda r y pi by 2 plus phi g. Then we have rotation by omega phi kappa, and then we have the observations in body reference frame. So, Lx, Ly, Lz plus r alpha 0, beta 0, gamma 0 into r x eta into 0, 0 r. That is the equation we have here. I would like to indicate that the measurement was in the instantaneous reference frame. This is the rotation between the instantaneous reference frame to scanner reference frame, and this is the rotation between the scanner reference frame to the body reference frame, and then we measured this lever arm offset in the body reference frame, and finally, this whole quantity was in the body reference frame. And then we converted this quantity by rotation, and then we have added the aircraft trajectory coordinate and then we brought this one, and which is the coordinates of the point P with respect to the geocenter of the earth. So, this equation is the geolocation equation or geolocation lidar equation. Let us see how to use this equation to determine the errors of the lidar data. We know that there is a GPS, there is IMU, there is an aircraft, and there is a scanner, and all four elements of the airborne data acquisition are contributing errors to the laser point data. and we want to estimate what is the error in the laser point xp, yp, zp. This is the error ellipsoid and we want to estimate this 2 times of sigma p, where sigma p is planimetric error, and 2 times of sigma v, where sigma v is vertical error. And here the point xp, yp, zp is located. So, I want to find out what is error ellipsoid here. Finally, the purpose is that the user generally defined maximum allowable error EP and EV in the planimetric and vertical direction. So, these errors sigma p and sigma v should be less than these values. That means I should acquire the data in such a way that sigma p and sigma v should be less than the maximum allowable errors demanded by the user. So, let us look into the process of error determination. We have defined earth tangential reference frame, where this was x axis here, this was y axis here, and this was the z axis in the gravity direction. We flip the z axis like this, and x and y axis, that means y axis come to the north axis, x into the true east, and z in the opposite to gravity direction. So, it is an orthogonal reference frame located at the aircraft trajectory. Let us translate it like this. So, I got coordinates of point P with respect to this reference frame, which is green but located at the geocenter. And what is the purpose of this? We want to analyze the errors in the green reference frame but located at the geocenter. For each and every point, this reference frame will be changing, because for each point we have different trajectory points, and each trajectory point has different direction of true north, true east, and gravity. So, by that I can analyze the data in a true manner. What does it mean by true manner? True manner means at a point P or at a trajectory point, whatever the gravity direction is there, what is true north and what is true east, and accordingly I am getting the coordinate of point P. So, in that frame only I want to analyze each and every point. So, I will have for each and every point a different reference frame at the center of the earth. Let us do it for one point. So, I can write this reflection as well as transformation matrix. Our inclination and reflection is indicated by this 0, 1, 0, 1, 0, 0, 0, 0, minus 1. Here you can see that I am changing x to y and y to x here, and as well as we are flipping over the z axis by minus 1, and then we are doing the translation by the x0, y0, z0 like this. So, let us write the equation which we have modified: x, y, z, eta f dash, and the origin at geocenter equal to x0, y0, z0 plus r, this matrix, into this r omega phi kappa, and then we have Lx, Ly, Lz plus gamma 0 eta 0, 0 r. In the above equation, you can see that we are doing the analysis for each and every point individually, and now I want to use the law of error propagation. To find out sigma xp, sigma yp, sigma zp. So, sigma p will be equal to sigma xp square plus sigma yp square, and sigma v equal to sigma zp. xp, yp, zp, and this is derived for the purpose of error analysis only. We are writing this xp, yp, zp like that. What are the parameters here, or what are the variables that we measure. First is aircraft trajectory coordinates, then we have omega phi kappa, lever arm offset, and then we have alpha 0, beta 0, gamma 0, then eta angle and the range R, where range is given by h into sec of eta. Eta is scan angle and h is flying height. We have to use the law of error propagation. Sigma xp, yp, zp is equal to a times sigma all these 14 parameters starting from x0, y0 to r into at. So, what is A matrix? A is Jacobian matrix. So, A is given by dou xp by dou x0, dou xp by dou y0, dou xp by dou z0, and now I write these terms with respect to all 14 parameters. So, I will get dou xp by dou x eta, dou xp by dou r here. Similarly, I will get here dou zp by dou x0, dou zp by dou y0, and finally I get the last term as dou zp by dou r. So, the size of this matrix would be 3 rows 14 columns. What about the sigma x0, y0, z0, eta and r? That will be 14 by 14, and we believe that all these parameters are uncorrelated. So, we have only diagonal elements like this. And rest of the elements are 0 here. So, now using the law of error propagation, I can find out the values of errors. That means, we have determined sigma xp, sigma yp, sigma zp. You may find this process very complicated if you are doing it using the manual calculation. So, use symbolic mathematics, use Microsoft Mathematics and try to write these equations there, then differentiate it, find out the A matrix, use symbolic multiplication and find out the complete expression of errors. What about the values of these variables? So, I am going to share typical values. GPS trajectory coordinates are generally having 5 centimeter errors because the sigma h0 is given as 2 centimeter plus 1 ppm, and we have the baseline equal to maximum 30 kilometers. So, if you calculate, you will get this value. What about the sigma z0? It is 1.5 times sigma x0 or y0. So, it is 7.5 centimeters. And now you can see sigma z0 is generally given by 2 centimeter plus 2 ppm. You can also calculate this value. What about the errors of the omega phi kappa? If I take some IMU model, let us say Applanix 510 IMU, it has values sigma omega sigma phi equals to 0.005 degree and sigma kappa is 0.008 degree. What about the values of omega phi kappa? Generally, we take omega phi kappa equals to 0, and you can take original values also if you have, but for time being you assume 0 degree. Then we have the bore side values. These values are generally 1 to 2 degree. So, we take 2 degree for worst case. And what about the sigma alpha 0? So, these are the typical values. What about the lever arm components? So, the typical values of the lever arm is 0.5 meter. What about the sigma values? .02 meter or 2 centimeters. What about the range and scan angle? Range you can measure as h sec eta, where eta is scan angle, and sigma r is a 2 centimeters or 0.02 meter. Sigma eta is this value, and there is a reason for that. We have considered the resolution of the scanner as well as we have considered the footprint angular value. So, by this we have calculated this one. Generally phi r is 0.002 degrees. So, if you put all these values, you will find out that sigma xp square plus sigma yp square, that is sigma p, generally comes out around 15 centimeter, and sigma v, which is sigma zp, comes out around 7.5 to 8 centimeter. So, you can see here that the error in the vertical direction of LiDAR is much lower, or 50% of the error in the planimetric direction, and that is the beauty of the LiDAR compared to the photogrammetry or GPS. In case of photogrammetry and GPS, you might have observed the vertical error are twice of the horizontal error or planimetric error is. In case of LiDAR, it is completely reverse, or I can say that LiDAR is more accurate in vertical direction. So far we have considered the plane as horizontal plane. What about the errors on the inclined plane? So, now let us see, this is inclined plane and there is a laser scanner. This is the center point or the range R here, like this. So, this is beam divergence. As a result, it will create an error ellipsoid, which is also inflated, or the size of the ellipse will be increasing, and this is 2 sigma p. So, what about the sigma z? The sigma z has increased. So, sigma v, the vertical error is given by sigma zp, that you have determined from the error propagation logic. Sigma p again from error propagation logic, and this tangent of alpha. Sigma v has increased in case of inclined plane. So, you should be careful if you have some hilly terrain where the hills are highly inclined, that means alpha values are very high, then you have to consider the error in the vertical direction, and that will increase because of the tangent alpha factor as well as sigma p here. So, you have estimated errors, but you want to verify errors in the real field. So, there are two ways to verify the error. The first is relative error. In case of relative error of one swath, we try to fit a plane to the particular swath data. For the given data, which is like this, few of the data in the plane and few may be lower than the plane, few may be above the plane. So, I have fitted a plane. Now, I will determine this error for this point, this error for this point, let us say this error for this point. So, all these errors I will determine and I will report the RMSE Z as relative error, and this relative error as per the mapping agency should fulfill some criteria. What about the absolute error? In case of absolute error, I will first transform complete LiDAR data into the geocentric reference frame ITRF, and then I will do some analysis. So, what kind of analysis I should do there? So, let us look into this thing. Using the data points, I will first create the tetrahedron or 3D tin, and then I will go to the field and I will measure the few of the points using GPS or total station, which is more accurate than the LiDAR data. Let us say I have measured all these data points. This is x, y, z from GPS. I call it reference data because it is more accurate. On the other hand, I have the data of the LiDAR. So, that is x, y, z by the LiDAR. Now, I will use the x, y of the reference and then I will put it here. Then using this tetrahedron or 3D tin, I will find out for this x, y value what is the z value interpolated by this triangle. So, let me call this z LiDAR that I determined by this x, y value, and then I will use z reference of this point because I have already observed this point by GPS, and then I will make the estimate of the RMSE-Z. So, I have determined this RMSE-Z. Now, I have to report this error also, but in case of LiDAR we have some different characteristics of different length types. Considering those length types, we have defined 3 types of accuracies like this. The first is the fundamental vertical accuracies. Fundamental vertical accuracies are determined on the surfaces which are horizontal as well as which are flat, like concrete surface, rooftops, stone surface, plain ground, basketball courts and so on. The error on such surfaces follow the normal distribution. So, what will I do now? I have taken such areas, I have collected GPS points and I find out RMSE-Z. Now, using that RMSE-Z, I will report fundamental vertical accuracy by this logic. That means, I am reporting the 95% error or accuracy I am reporting. Now, let us consider some other areas where errors are not normally distributed. Such areas are vegetation, trees, grass ground or grasslands and so on. So, in such area we define supplemental vertical accuracy using 95th percentile of RMSE-Z. But before looking into how to find out 95th percentile, we will first define one more error accuracy criteria called consolidated vertical accuracy. What is the CVA? Let us integrate all the areas which follow normal distribution of error or non-normal distribution of error. Let us see, we have football ground, basketball court, concrete tops, concrete rooftops, stone surfaces as well as vegetation, grassland, shrubs. Now, collect some n number of points using GPS or maybe total station on this complete area, and then you define RMSE-Z. Using that RMSE-Z which is on the combined area, find out the 95th percentile of that errors, and then you will say that 95th percentile will be consolidated vertical accuracy. So, these are the 3 criteria we define. Now, how to define the 95th percentile, that we have to see. Let us say you have 1000 GCPs taken by total station or GPS. For these 1000 GCPs, you have determined the errors and you are writing those errors in the ascending order. Let us say E1, E2, E3, E1000, where E is Z LiDAR minus Z reference, or you may be taking the mode of that. So, you have determined these errors and then you will find out where is your E950, that is the 95th percentile. And then you will report this E950 as accuracy or the error of LiDAR data. So, that is accuracy here. So, this is the way we determine the accuracies. Now, we finish this lecture here, and in the next lecture we will try to find out that how can we extract the information using the LiDAR data which is already available in a reference frame, let us say ITRF. Thank you very much.